Hi, my name is Arish Virani, and this is my Physics 2211 Lab 1 on constant velocity. So the purpose of this lab is to observe and predict the one-dimensional motion of an object that is moving at a constant speed in the same direction, hence the object has a constant velocity. This will enable us to demonstrate the principles of Newton's second law of motion, which is also known as the momentum principle. This suggests that we can predict the final velocity of the object, as since the net force of zero is acting on this object of constant mass, velocity remains constant. The main result of this lab is proving the physics regarding the net force acting on an object, along with its velocity and motion. We will also be able to visually understand how a net force of zero acting on an object leads to constant velocity and how to represent constant velocity of observed and predicted motion graphically. We will also understand why there are small differences between the velocities or slopes of the predicted and observed motion due to the lack of a true net force of zero acting on the object. The physics principles and formulas that we'll be using, Newton's second law, the momentum principle. This defines the net force to be equal to change in momentum with respect to time or per change in time. We can rewrite this formula to predict final velocity and momentum. This principle and these rewritten formulas clearly show that when the summation of all forces acting on an object is zero, net force is equal to zero, the momentum and thus velocity of an object would remain constant. Final velocity equals initial velocity. As a result, the formula can further be rewritten to predict the final position using average velocity. So for our procedure, we have a video recording of an object sliding in one direction across a flat surface, one-dimensional, at a constant speed. We analyze the object's change in position over a period of time using the tracker software. This allows us to determine the observed linear motion or constant velocity. We use relevant data like initial position, average velocity, change in time per iteration, delta t, net force, mass, Newton's second law formulas for velocity and position updates for GlowScript's computational code, and predicted model. We use Excel for graphing both predicted and observed models to compare trends. Finally, we analyze the results and make conclusions from data and trends. So this is our object, the cart, the observed position model software that we're using tracker, and the predicted position model software, the GlowScript computational code. Here's the setup. This is a fixed camera with one-dimensional motion across the frame. The system is the cart, and the surroundings include the earth, track, air, and the hand during the brief launch. I used a 0.167 meter calibration stick, front and center, and defined plus y state as the upwards direction. The tracker software then gave me time position data by marking the cart each frame. This is the observed position time plot. The trend is not exactly linear, as you can see, but the best fit line is nearly perfect, indicating constant velocity. For comparison with predicted motion, I made the 2.867 seconds our initial t set to 0 seconds, and made the 3.267 seconds the final t, which is equal to 0.4 seconds. I then calculated the average velocity with the following formula using two positions and timestamps from the previous observed recordings. This gave me a change in position of minus 0.133 meters, with the corresponding change in time of 0.266 seconds, and an average velocity of minus 0.5 meters per second. For the GlowScript computational model, I set the initial position match the data and velocity to fit its slope, so the initial position is minus 0.156 meters in the y direction, and the initial velocity is minus 0.5 meters per second in the y direction. Meanwhile, the initial time starts at 0 seconds, with change in time per iteration being 1 upon 30 seconds. The final recorded time is 2 seconds, however, for comparison with the observed motion, we will use the values to 0.4 seconds. The net force acting on the object is assumed to be 0 newtons in all directions, and the mass remains constant at 0.5 kilograms. In each iteration, we use the velocity and position update formulas that we derived and rewrote from Newton's second law of motion. This is the result of running the code, and these are the final graphical results of both the observed and predicted motions. The assumptions and overall analysis. The observed and predicted motions are very similar graphically and appear to be linear. However, the observed motion slope or gradient does seem to be a bit more flatter or less than that of the predicted motion. As the slope of a position versus time graph equates to velocity, this would indicate the observed speed to be slower than what is predicted. This could be due to our assumptions for the predicted motion that the net force acting on the object is exactly zero, which does not take into account opposing forces like friction and air resistance. The lack of these forces and a true zero net force on the object would cause the object's position to change slightly faster, and thus explain why the slope of the predicted motion is steeper than that of the observed motion. There could also potentially be human errors in tracking the object mass on the tracker software. Furthermore, there could be an error in rounding, which would lead to slight deviations of results. So what if and what does it mean discussion? What if we were to flip the axes? That is, if plus x and minus x were interchanged. So in our case, that would be from plus y to minus y due to the video recording and tracker software. So if we were to flip the axes, as it is now from minus y to plus y, the sign of the slope of the graph would become the opposite, which is positive. The position of graph distinguishes up to down as a negative slope and down to up as a positive slope when plus y is upward. After the flip, when plus y is downward now, those sign labels swap. The magnitude of the slope or the speed would remain the same. Is it possible for us to say how many pushes and pulls, how many forces are being added together to give zero net force in the case that we observed? We can't tell for sure how many forces there are from the motion alone, as seeing constant velocity only tells us that the vector sum of all the forces is equal to zero. What we can say for sure from our setup is that at least two forces are present all the time, including weight, mg downward, and the track's normal force, and upwards. For a level track, they cancel in the vertical z-axis direction, n is equal to mg. Along the direction of the motion, after release, there's typically no sustained push. Small resistive forces, friction, or air resistance or drag may act but are small, so the horizontal y-axis net is approximately zero. Many combinations can give us net force of 0, like nmg or nmg and some drag, or nmg some drag, and a slightly downhill component, etc. Hence, the motion doesn't let us count them, only their sum. In conclusion, taking into account all of these factors, when we see how the observed model differs from the predicted model that has a net force of 0 acting on the object, we can say that the object we observed did not have a net force of 0. In the predicted motion, when a net force of 0 is acting on the object of constant mass, the velocity remains constant.